Today we will discuss about the interference of light. Now, in last class we have discussed about the interference of light, and we have seen there that we have obtained a black and white image, or I can say bright and a dark image on the observation screen. And we have derived the expression for the intensity. This was the expression for the intensity, and this was the bright and the dark fringe obtained on the observation screen. Now, in today's class, we will study why do we obtain this bright and dark fringe. Now, let us start with the bright fringe. The bright fringe means your maximum intensity, or I can say when the two waves coming out of the two slit added up constructively, or they added up to construct a newer wave or newer light which has a higher intensity, then in that case you get the maximum intensity, and that condition is known as your constructive interference. That means you will have the maximum intensity, or I can say the bright fringe like this one and this one. Now, the other thing is, how can we show it mathematically? As we have derived your intensity I equals to I1 plus I2 plus 2 root over I1 I2 cos phi, where I1 is the intensity of the light coming from your first slit, I2 was the intensity of the light coming from your second slit, and this term represents your interference term. Now, for the maximum intensity, all of these three terms had to be maximum. It is possible that all these three terms will be maximum only if all of them are positive. As we know, intensity from the first slit is positive, so as the intensity from the second slit, this is also positive. But what about the third term? In this third term, do you see this term cos phi? So for the third term to be positive, this cos phi has to be positive. If cos phi is positive, only then we will get the bright fringe as shown here. Fine. So for constructive interference, the resultant intensity at the point P will be maximum when cos phi equals to 1 or phi equals to 0, 2 pi, 4 pi. What does this mean? So this is your cos wave curve. Now in this cos wave curve, the cos had to be positive. That means plus 1. Fine. So in this curve, this one represents your angle pi, 2 pi, 3 pi, 4 pi, and so on. And this one represents your cos. So cos of 0 is 1, cos of pi is also minus 1, cos of 2 pi is 1, cos of 3 pi minus 1. So this is the cos curve. Now for the constructive interference or for your bright fringe, the cos had to be positive, plus 1. And for which values your cos will be positive? It will be positive for 0, for 2 pi, then again for 4 pi and 6 pi. So what do you notice? We notice that whenever this angle is a even multiple, then your cos phi will be positive. So when phi equals to 0, 2 pi, 4 pi, and so on, my cos phi will be positive value, which is 1, and this is the maximum value for a cos phi. Now, since the phase difference of 2 pi corresponds to a path difference of lambda, therefore P is the path difference between the Therefore, if P is the path difference between the two superposing waves, then now in this part, this 2 pi, these angles 0, 2 pi, 4 pi, they all represent your path difference. Now what is a path difference? Suppose your light is traveling from slit S1 to point P and your light is traveling from S2 to point P. What you notice is that the light coming out of the slit S2 is covering some extra distance. Now, the extra distance covered by the light coming out of this slit S2 is known as your path difference. So, because of this path difference also, we will obtain the bright and the dark fringe on the observation screen. So from here we understand 2 points. The first point was my cos phi or my phi or my angle, which means the delay between these waves. The delay of the respective waves, if they are the even multiple of pi, like suppose 2 pi, 3 pi, 4 pi, in that case you will obtain a bright fringe at point P. Or I can also say that if this path difference is multiple of the wavelength lambda. What is the wavelength? Wavelength means this distance. The time a wave takes to complete one cycle. This is known as your wavelength. Now, when the path difference, this extra path will be the integral multiple of lambda. In that case also, we will obtain a bright fringe. Let's see how. So, as P is your path difference, we have said that path difference also depends upon your phase difference. So what I will do, I will write my path difference in terms of radians. So in terms of radian, it will be 2 pi P divided by lambda, which in turn should be equivalent to your phase in order to get your bright fringe. As we have studied, for this phase or for this angles, I will get the bright fringe. Fine. In that case, if this one 2 pi P by lambda equals to 0, in that case everything will go there and then I will get my path difference equals to 0. Fine. Now let us consider your second case when your path difference 2 pi P by lambda is equals to 2 pi. Now in this case 2 pi lambda will go here, so I have my path difference P equals to lambda. In that case also, the observation screen, on the observation screen I will obtain a bright fringe. Consider your third case when 2 pi P by lambda equals to 4 pi. In this case, this one will cancel this one by 2. This lambda will go here. So when my path difference equals to 2 lambda, in that case also on the observation screen I will obtain the bright fringe. So what do you notice from here? When my path difference P is 0 or lambda or 2 lambda or 3 lambda, bright fringe. Or I can say if they are the integral multiple of the lambda, in that case also I will obtain the bright fringe. Hence, the resultant intensity at a point is maximum when the phase difference between the two superposing waves is an even multiple of pi, or path difference is an integral multiple of the wavelength. This is the condition for constructive interference. Fine. Now, we have discussed about the bright interference. Now let us understand why do we get this dark interference. Now to obtain this dark interference, what is happening is that the wave coming up first slit S1 is being cancelled by the wave coming out of your slit S2, or I can say the wave from your slit S2 is destroying the wave coming out of your S1. So if they are destroying each other, in that case you have nothing on the screen. That means you should get a okay. You can understand it like this, or let us consider, suppose I is the intensity I1, I is the intensity I2, and this is your twice of I cos phi. So in this case, I1 and I2, they are of fixed values. They have to be positive. But I have said that the waves coming out of the second slit is cancelling the first one. And how is it possible? It is possible. The effect by these two terms is being cancelled by this third term. Fine. In that case, what happens? There is nothing on the screen and you obtained a dark fringe. So how can we obtain this condition? This condition can be obtained when this term will be negative. Fine. So for dark fringe, what happens? My cos phi term will be negative, and in the case of dark fringe, what happens? The two waves destroys each other, hence we can call it as destructive interference. So let us discuss the condition for destructive interference. The resultant intensity at point P will be minimum. Minimum means your lowest value. That means the smallest value. So it can be 0 or smaller than 0. Fine. The resultant intensity at P will be minimum when cos phi will be negative, or I can say -1. When will be cos phi negative? When phi equals to pi, 3 pi, 5 pi. Fine. So let us take a look at this curve. This is again your cos curve. Now when is your cos -1? It is -1 when angle is how much? Pi. When the angle is how much? 3 pi. When the angle is how much? 5 pi. So what do you notice here? My cos will be negative whenever my angle will be the odd multiple of pi. In that case, my phase will be negative. So cos phi equals to -1. Now just like our previous case, let us derive the condition for the path difference. So if P is your path difference and we are writing it in terms of your radians, then 2 pi P by lambda equals to pi equals to 3 pi equals to. So let us take a look at your first condition. In this case, pi and pi gets cancelled, lambda will go to the numerator, 2 will go to the denominator. So I have path difference equals to lambda by 2. Now what does this mean? If the light is coming out of the slit S1 like this, and the light coming out of the slit S2 is like this. Fine. Now this is up till here it is lambda, up till here it is lambda. Again from this point to this point it is lambda. Again from this point to this point is lambda. Now in this case it is traveling a distance half of a wavelength, lambda by 2. But in this case it is traveling a full wavelength, lambda. Now what will be the difference of lambda 2 and lambda? It will be this half wave. This is the extra wave, or I can say this is the extra phase. Phase of how much? Pi. Because of this extra phase, there is an extra path difference coming into a picture, And if there is an extra path difference coming into picture, what happens? These two waves superpose each other and the resultant wave will be nothing. Therefore, you will obtain a dark fringe. Fine. Similarly, let us consider your second case. 2 pi p by lambda equals to 3 pi. In this case, again pi gets cancelled. Lambda will go to the numerator, 2 will go to the denominator. So if path difference equals to 3 lambda by 2. Now in this case, if path difference equals to 3 lambda by 2, what does this mean? Well, lambda by 2, lambda by 2, lambda by 2. If the light coming out of the slit S2 is covering this much of extra distance as compared to the light coming out of the slit S1, then in that case also we will obtain the dark fringe on the screen. Now similarly, your last state, pi gets cancelled, lambda will go to the numerator, 2 will go to the denominator. So when path difference equals to 5 lambda by 2, in that case also you will obtain the dark. So if phase angle is an odd multiple of 5, then in that case you will obtain the dark fringe. Or I can say when the path difference, when the extra path travel is odd multiple of this lambda by 2. Do you notice this lambda by 2? All of them has this lambda by 2. But there is a odd number in front, 1, 3, 5, 7, 9 and so on. So when your path difference will be the odd multiple of lambda by 2, in that case also you will obtain the dark fringe. Fine. So I can write this odd number as 2n minus 1. 2n is your even number. If I subtract 1 from it, I will get a odd number. So hence the resultant intensity at a point is minimum when the phase difference between the two superposing waves is an odd multiple of pi, or the path difference is an odd multiple of lambda by 2. So this condition is for destructive interference. Fine. So that's it for today's class. Thank you. If you have any confusion, please don't hesitate to ask. I will re-explain it to you again.